Hello, I'm here with another video related to the topic of power and efficiency. Before I get started and talk about the problem, I just want to let you know that this would be my first video actually that I'm using an iPad Pro with the nice pencil that comes with it. And hopefully my handwriting is going to be much better now because so far all the videos I've made I've been using my finger. Special thank you to the department head of the interdisciplinary at Wentworth Institute of Technology, Dr. Albers, for providing this iPad Pro and the pencil. So let's get started. Here we have this pulley system which is designed to move the load at A. So if we say the load at A, given that the weight of A is 100 pounds, right? And you see the motor here putting so much tension in the cord. And we know actually the speed of the cord is 3 feet per second. Let's say if we know the motor is 80% efficient, so we know the efficiency is 80%, where epsilon is 0.8, right? And if the objective is to move this load up, right, with a constant speed. So the velocity, actually, this motor is going to create a constant tension at a constant speed of 3 feet per second. What would be the power input? What would be the power that is required to do this? In other words, if this motor is an electric motor and we plug it into an outlet, how much power we'll be drawing in? So our objective is to find the power input. And preferably we want to put that in horsepower. Okay, so let's get started. We know that the definition of efficiency, epsilon, is power out divided by power in, power output divided by power input. So having the efficiency, if you want to find the power input, this is the unknown, I have to calculate the power output. So the power output for a problem like this can be calculated by simply saying that if you could find the tension in this cord, T, or we can put it this way actually, that tension actually is going to be the force, and if you take that tension or the force in that cable and we multiply it by velocity, which is 3 feet per second, that's how we're going to calculate actually the power output. So this is basically the tension in that cord times velocity. So notice that that tension here, if you look at the free body diagram of this, it's going to be T over 2 here and T over 2 to balance the T. So actually the tension that is acting on this cable here would be T over 2. So if we now draw a free body diagram of this load where this tension is T over 2 and the weight is 100 pounds, notice that the velocity is constant. So this is moving with a constant speed. If velocity is constant, the acceleration then would be 0. Therefore, this load is, even though it's moving at a constant speed, but it's going to be in equilibrium. So if you just use the second law, sum of the forces in y equal MAY, we'll pick this to your positive direction, right? So we have T over 2 minus 100 equals 0. So T would be equal to 200 pounds. So having determined T of 200 pounds now, if you take that and we multiply it by the speed here, which is 3 feet per second, that will determine the power output. So I'm going to move it down here and say power output now is 600 pound-foot per second. Now you guys know the conversion factor. You know that 1 horsepower is equal to 550 pound-foot per second. Therefore, if you want to get this in horsepower, just divide it by 550. So that is about 1.091 horsepower, almost 1.1 horsepower. And remember, that's the power output. This motor is 80% efficient. So now that means obviously what you have to put into the system is going to be larger than 1.091 horsepower, because, 20% of the energy basically is lost. So using this formula here, we can say then the power input is equal to power out divided by efficiency. So if you take 1.091 horsepower and divide by 0.8, you end up getting about 1.36 horsepower. So basically you're drawing in, if this was an electric motor, if you plug it into the outlet, and you're drawing in 1.36 horsepower, which is, if you actually want to convert this to watts, you have to multiply it by 746. 1 horsepower is about 746 watts. So then that's about, in the neighborhood of 1100 watts or so. Okay? So hopefully I'll come back with more videos on power and efficiency and other topics. Thank you for watching and listening.